Hey, I'm Jinjie Mai, currently an undergraduate from Sun Yat-sen University. Today I'll introduce our CPU-powered work, Erasing Integrated Learning, a simple yet effective approach for weakly supervised object localization. Firstly, I'd like to introduce the task of weakly supervised object localization. For the task of object localization is a bit similar to object detection, which aims to draw bounding boxes for the object. However, object detection is for multiple objects, while object localization is only interested in a single class. In weakly supervised refers to that there is only weak labels available in the training dataset. So in our object localization, it always means that there is only image labels in the training dataset without pixel level bounding box annotations. Class activation map is a popular baseline for weakly supervised object localization, proposed to replace top layers with global averaging pooling in CNN training for classification. In this pipeline, the bounding box on the image is generated after thresholding and contour finding on the CAN map. However, although the modified CNN is able to locate the object, there is a critical issue that the CAN map always highlights the most discriminative regions instead of full extent of object, resulting in the limited performance in object localization. For this problem, a bunch of methods have been proposed. An adversarial erasing is a very popular approach among available techniques. The key idea is that without the guidance of the most discriminative area, the network will be forced to classify the object by exploring more insignificant areas. On this basis, most of these techniques can be roughly divided into several classical types as shown in the image. Stem-wise erasing trains a convolutional network at first to mark the most discriminative regions, then perform the erasing operation and retrain the entire network, but additional training step can lead to expensive computer overheads. Another popular method is multi-branch based erasing approaches, which introduces new branches into the network to perform erasing. Such approach is more efficient than stem-wise erasing, but it requires to modify the backbone network and introduce extra parameters. Most recently, random erasing approach has been proposed, which stochastically erases the most discriminative regions in forward propagation. Without actual network computation, such an approach can save quite a few computation and parameter resources. However, random erase is still limited by classification degradation because the random dropout will lose informative regions. So to this end, we have proposed with erasing integrated learning for the task of weakly supervised object localization. Left image has shown the detailed structure of our EIL, erasing integrated learning, and the right image have shown the overall structure of EIL. In general, EIL is added between convolution blocks of CNN in a sequential way. During training, taking the following feature map as input, we generate the erasing mask and remove the most discriminative regions on the feature map according to this mask. Then we feed both erased and unerased feature map into the next convolutional block, which will create two data flows. As such treatment can also be regarded as a dual-branch network with shared weights, so the final loss is produced by the two classification loss from the erased feature map and the unerased feature map, respectively. And here we explain the conceptual theory of our work. Through the erased loss, the network can learn to classify the object by means of the most discriminative region. At the meantime, the erased loss drives the network to focus on the less discriminative part to explore the complementary object region. The rightist image has shown the visual evidence of our explanation. It can be observed that in Great CAN, at first the network only learned the most discriminative regions, like the health of the bird. Gradually, the upcoming gradient from erased branch gradually releases the unerased branch to cover the full extent of the object, including the less discriminative regions, like the torso of the bird. We can even drive our method further. While existing erasing approaches chose to erase in a single location, we propose in advance multiple ELL modules to perform erasing at multiple locations. Multiple erasing can have many variants because it has many locations to insert. These slides have shown two of them. In this way, multi-scale or visual patterns can be learned adversarially and simultaneously. As a result, the network will produce more loss from shared branch, can lead the network to explore the object of interest from multi-level, not just the finest features for classification, so we can get a better localization performance. These slides have shown the final visualized result. Our approach can produce more integral heat map to fully localize the object. Our methods achieve new SOTA results. Thank you for